In today's notes, we're going to take a look at how to find something called the determinant of a square matrix. Now, the first thing that I want to point out here is that your matrix has to be square. So that means that it has to have the same number of rows and columns. For us in this class, that means we'll only be looking at 2x2 matrices and 3x3 matrices. However, there is a process for going to matrices that are bigger than that, but we're only going to stop at 3. The first thing that I want to do is I want to tell you what a determinant is. So a determinant is a single numerical value that is obtained from a matrix by multiplying the numbers along its diagonals. So the next thing we need to talk about is what is the notation for a determinant? So what are you going to see that's going to let you know that they expect you to take a determinant? So there's actually two different notations for this. Let's say you have a matrix A. One notation that you might see that's telling you they want you to take the determinant is you might see what looks like absolute value signs around that. So you see absolute value signs around the name of a matrix, which would be a capital letter of some kind. That means they want you to take the determinant. That's kind of the older notation. The newer notation is that they would actually just say DET, which is an abbreviation for determinant, and then they would put the matrix that you want to take the determinant of inside of parentheses. So either one of these notations would be letting you know they expect you to find the determinant of matrix A. For a 2x2 matrix, there's only 2 diagonals that you need to concern yourself with. So let's take a look at what a 2x2 matrix might look like, and then what they're going to want you to do to find the determinant. So down here I've got a matrix W is its name, and you can see I've left inside of it the values in all 4 of the spots kind of in generic A, B, C, D. So the 2 diagonals that we're going to be looking at are this one going from the top left corner to the lower right corner, and this one going from the lower left corner to the upper right corner. Any diagonal that's going in this direction, from the upper left to the lower right, is considered to be going in the positive direction. So whatever the product is going in that direction, you're going to leave whatever the product is alone. If it's positive, you're going to leave it positive. If it's negative, you're going to leave it negative. However, the diagonal that's coming back in the opposite direction, from the lower left towards the upper right, this diagonal is considered to be going the wrong way. And therefore, whatever the product is along this direction, you're going to negate it. So if somebody asked us to take the determinant of matrix W in this problem, I would start by multiplying A times D. That's my first diagonal, and whatever that product is, I'm just going to leave it alone. Whether it's positive or negative, I'm just going to not touch it. And then I'm going to subtract the product of the diagonal along the other direction. So C times B. So this is how you find the determinant of a 2x2 matrix. Okay, so let's practice what we just learned on a few 2x2 matrices. Our first matrix is going to be called matrix C, and its values are 2, -3, 1, 2. And when you see this notation right here, this means they want you to find the determinant for matrix C. So we're going to start by multiplying the numbers along this diagonal, and 2 times 2 is 4. Whatever that product is, we're just leaving that alone, 4. Now, we're going to multiply the numbers along this diagonal, which is 1 times -3, which is -3. But because that diagonal was going the wrong way, we are subtracting that. So you actually end up taking 4 minus a -3, which leaves us with an answer of 7. Our second matrix is going to be matrix D, and it has the values 0, 3/2, 2, 4. And this means the same thing as what you saw up here. It's just the newer notation, determinant of matrix D. Again, that means they want you to multiply the numbers along this diagonal first. Remember, 0 times anything is 0. And then you're going to multiply the numbers along this diagonal. 2 times 3/2 is 3. But because it's going the wrong way, we're going to be subtracting that. So that gives us a final answer of -3. 0 minus 3. Last matrix is called matrix E. And again, they're going to ask us to take the determinant of it. When I multiply the numbers along this diagonal, I'm going to get 2 times 2, which is 4. Whatever that product is, you just leave it alone. And then I'm going to multiply the numbers coming back in the opposite diagonal direction. 4 times 1 is 4. But again, it's going the wrong way. That diagonal is going the wrong way, so I have to subtract that. This leaves me with a final answer for my determinant of 0. Now, by the way, I'm going to tell you, if you do end up getting a problem that has a determinant of 0 that has a very special meaning, that means that matrix is a singularity. And if you recall from our previous notes, what that means is this particular matrix, even though it's square, does not have an inverse. So any matrix whose determinant is 0, if we tried to find the inverse of this matrix, end up giving us a row of all zeros and therefore lead to having a singularity. For a 3 by 3 matrix, things get a little bit more complicated because for a 3 by 3 matrix, there are actually 6 diagonals. Now I know when you look at a matrix, this is a generic matrix that just has the letters A, B, C across the top row, D, E, F across the middle row, G, H, I across the bottom row. You can see there's 3 rows and 3 columns here. So this is a 3 by 3 matrix. It is very difficult to see all 6 of the diagonals. The person who invented this, I'll show you the way they did it. This is one diagonal, A times E times I, and then this person practiced like wrapping around. So the next diagonal would be B times F, and it would wrap around to G. And the next diagonal would be C, and it would wrap around to H and D. That's only 3 diagonals, by the way. The other 3 diagonals head in the opposite direction. You've got G times E times C, H times F wrapping around to A, and I wrapping around to B and D. Now, this is very confusing for most people. So this is not the way we're going to do it, but that's the way the person who invented this did it. What we're going to do instead, I'll show you a little trick. We're going to copy the first 2 columns next to the matrix. This is going to make your job of completing all the diagonals a lot easier. So this is my first column. This is my second column. What I want you to do is copy those 2 columns, ADG and BEH. Copy those first 2 columns next to your matrix. And what that's going to allow you to do now is to actually complete all 6 of your diagonals without doing that crazy wrapping around thing. So we've got 3 diagonals heading in this direction from the upper left to the lower right, and 3 diagonals heading in this direction from the lower left to the upper right. Again, any diagonal that's headed downward from left to right is considered to be going the correct way, and therefore you leave the product alone. And any diagonal that's coming back from lower left to upper right is considered to be going the wrong way, so we'd be subtracting all of those. So here's what you get when multiplying along the diagonals here. You're going to get A times E times I, that's our first diagonal, added with B times F times G, added with C times D times H. Now those are the diagonals going this way. Then you're going to be subtracting the 3 diagonals that go the wrong way. So that's G times E times C minus H times F times A and minus I times D times B. So 3 diagonals going in the correct direction, add up their products. 3 diagonals going the wrong way, subtract their products. And whatever number this produces, it will be one singular number when you get done doing all that math. That represents the determinant for this 3 by 3 matrix. So let's practice on a few examples now. So here we have matrix F, which has 1, 2, 3 rows and 1, 2, 3 columns. So this is a 3 by 3 matrix. If you're being asked to find the determinant for matrix F, you're going to want to take the first 2 columns here. So the 0, 3, 4, which is my first column, copy it next to it, and the second column, 2, -1, 0. So now you're going to want to find the 6 diagonal products and put them all together to make one single number. So my first diagonal, 0 times negative 1 times 1, is going to be 0. My second diagonal is going to be 2 times 2 times 4, which is 16. And my third diagonal is going to be 1 times 3 times 0, which is 0. So those are the 3 diagonals that you take the product and you don't change their sign. Just whatever it is, just add them up. 0, 16, 0. Now these diagonals coming back the wrong way, you're going to be subtracting. So this diagonal's product will be 4 times negative 1 times 1, which would be negative 4, but you're subtracting negative 4. So that actually has the effect of like adding. My next diagonal going the wrong way is 0 times 2 times 0, which is 0. So we'll be subtracting 0. And then 1 times 3 times 2, which will be subtracting 6. In the end, when we put all of our numbers together, we're going to have 16 plus 4, which is 20, minus 6 gives me a final answer of 14. Last one. This, again, is going to be matrix G, and it has 3 rows and 3 columns. If somebody asked you to find the determinant for matrix G, and I'm going to use the older notation here with the absolute value signs, first thing you ought to be doing is copying the first 2 columns next to this. So negative 3, 4, 2 is copying over the first column next to my matrix. And then 2, 5, negative 3 is copying over my second column next to the matrix. Okay, here we go. Negative 3 times 5 times 1 is negative 15. So whatever the products are when you're going in that direction, you just leave it alone. If it's negative, you leave it negative. So that's negative 15. Don't touch that sign. The next one is going to be 2 times 6 times 2, which is 24. So we'll be putting that together with the negative 15. And the last one is going to be 1 times 4 times negative 3, which is negative 12. So remember, when the diagonals go this way, it doesn't mean your answer is going to be positive. It just means you're not going to change the sign. So if they're negative, leave them negative. Now the products coming back the opposite way, whatever they're going to be, you're subtracting them. So this was 2 times 5 times 1, which is 10. We're subtracting 10. This was going to be negative 3 times 6 times negative 3, which is going to be 54. We're subtracting 54. And the last one, 1 times 4 times 2 is 8, but we're subtracting 8. Okay, so now we just got to put all those numbers together. So we've got positive 24, and putting these two together would be negative 27. So far we're negative 3, negative 13, negative 67, negative 75. So your final answer here for the determinant of this matrix was negative 75. Okay, you are now ready to give the homework for tonight a try.